Hello children, welcome. This is Crash Course and we are discussing system of particles and rotational motion. First we will discuss the important concepts, equations and the ideas relating to this chapter. To begin with, let us take up the idea of center of mass. What is center of mass? Suppose I consider center of mass is that point at which the total mass is assumed to be concentrated. Simple. It is that point at which the total mass is assumed to be concentrated. So it is that point at which the total mass is assumed to be concentrated. Let us consider first of all center of mass of a system of discrete particles. Let us consider the representation like this. This is x-axis, here is y-axis and this is z-axis. Consider a couple of particles m1, m2, m3 and so on. m1 has a position vector r1, m2 has a position vector r2, m3 has a position vector r3, etc. Their coordinates are x1, y1, z1, x2, y2, z2 and x3, y3, z3. We can consider many such particles. This is origin, of course. Then the center of mass of this system is given by m1 r1 plus m2 r2 plus m3 r3 whole divided by, of course there are many particles, we can write it this way, divided by m1 plus m2 plus m3 etc. This can be written like this: sigma mi ri from 1 to n whole divided by sigma mi from 1 to n. The denominator is the total mass of the system, so I can simply write as sigma mi ri from 1 to n. This can be broken up into three parts, one along x-axis, the other along y-axis and the other along z-axis. So we have xcm is equal to total mass sigma mi xi from 1 to n. Then ycm is equal to 1 by m sigma mi yi from 1 to n. Likewise zcm is equal to 1 by m sigma mi zi from 1 to n. So for a system of discrete particles, this is how you find the center of mass. But what if it is a continuous mass? What if it is a continuous mass distribution? For example, we have this arrangement. You can consider this as x-axis, y-axis and z-axis, and you have a continuous mass distribution like say a rigid object of this form. Then assume that its mass is m. This is origin. Then what you do is you are going to consider a small mass dm whose position vector is r, and you are going to find the center of mass by considering it like this: 1 by m integral r dm, and you can integrate it to get your xcm, ycm and zcm. 1 by m integral x dm ycm is equal to 1 by m integral y dm, and zcm is equal to 1 by m, where m is the total mass, integral z dm. Right? So it is a very simple idea. Here remember x, y, z are the coordinates of the mass which we have selected with reference to the origin. Simple thing. Suppose I consider, say, an object from which a part is removed. Center of mass of an object after the removal of a part. Here it becomes something like this. Suppose the original mass is m, mass removed mass is small m, say, then the new formula or the formula changes to xcm is equal to mx minus mx dash divided by m minus m. Ycm is equal to my minus my dash divided by m minus m, and zcm is equal to mz minus m z dash divided by m minus m. These are already known to us. What are the other three? X, y and z refer to center of mass of the original part. That means the object from which nothing is removed. X dash, y dash and z dash are cm of the removed part, the part which is removed. So you can find out the xcm and ycm and zcm using this idea of if part is removed from the object. Let's just recall center of mass of some important shapes. For example, half ring, something like this. Let's assume that this is x-axis and this is y-axis, this is the origin, then the center of mass is here at a height, say y, and this y is given by 2r divided by pi, r being the radius, Segment of a ring, something like this, a symmetric segment. This is again x-axis, this is y-axis, etc. and this angle is theta, and this is at a height y, say, then radius is of course r, then the center of mass is located at a height r sin theta divided by theta, A half disc, for example, let us consider a half disc like this. Remember, this is a disc or plate. This is of radius r, this is x-axis, this is y-axis, etc. and it is at a height y. Y is given by 4 by 3 r divided by pi. This is for a half disc. Suppose I consider sector of a disc, a symmetric one, of course, asymmetric, a symmetric one, not asymmetric, x and y. This is theta, and the center of mass is at a height yc. Then this is given by 2r sin theta divided by 3 theta. I urge you to remember them. A hollow hemisphere, assuming it to be at a height of y, then y is given by 3r divided by 8, r is the radius. Sorry, this is a hollow hemisphere, this is r by 2, I am sorry, this is r by 2, hollow hemisphere. While for a solid hemisphere, y is given by 3r by 8. This is solid. For a solid one it is 3r divided by 8, while for a hollow hemisphere it is r divided by 2. Remember, these are measured from the center. A hollow cone of height h, and this is x-axis, etc. From this point assume that center of mass is at a height y, so y is equal to h divided by 3. While for a solid cone, this is a solid cone of height h, and again this is x-axis, this is y-axis, etc., and this is at a height y, then y is given by h divided by 4. So I urge you to remember these values, worth remembering, because you may not be able to derive this all the time. It is these equations are worth remembering instead of trying to derive them all the time. Remember, don't try to derive them all the time. Okay, suppose I consider motion of center of mass. What happens, how to find out, how to analyze, etc. Now for a system of particles, velocity of center of mass is nothing but the derivative of position of center of mass. So this simply becomes m1 v1 plus m2 v2 plus m3 v3, etc., whole divided by m1 plus m2 plus m3 and so on. What if I consider acceleration? Acceleration of center of mass is m1 a1 plus m2 a2 plus m3 a3, etc., whole divided by m1 plus m2 plus m3. Now actually if you look at this equation, you notice that d by dt of m into VCM, is nothing but force. That's actually external force. So if external force is 0, then we notice that m into VCM is equal to constant. That is nothing but the law of conservation of momentum. For a system of particles, the law of conservation of momentum tells us that the velocity of the center of mass is unaffected by internal forces, or if the external force is 0, the center of mass remains fixed. So these are some basic ideas regarding the center of mass. Now let us take up the idea of the rotational motion of rigid bodies. So let's just recall some basic equations, basic idea. Angular velocity, is given by d theta divided by dt, a vector quantity. Angular acceleration is given by alpha, which is d omega by dt. This can also be written as d square theta by dt square. Angular momentum is nothing but r cross p, that is I omega. And the rotational analog of force, which is torque, is given by tau is equal to r cross f, and this can also be written as the rate of change of angular momentum dl divided by dt. And the rotational kinetic energy, is given by k is equal to half I omega square. In terms of angular momentum, this is given by L square divided by 2I. The equations, suppose I consider constant angular acceleration, then the equations of rotational motion can be written like this: omega is equal to omega naught plus alpha t, theta is equal to omega naught t plus half alpha t square, omega square is equal to omega naught square plus 2 alpha theta, and theta n is equal to omega naught plus alpha divided by 2 into 2n minus 1. This is the distance travelled or angular displacement in the nth second of the journey. A couple of important informations in the present context are like this. So what are those things? Let's try to understand. Suppose I consider the idea of torque. Torque is nothing but quantity which produces angular motion. Just like force produces angular acceleration, torque produces just like force produces linear acceleration, torque produces angular acceleration. Now, if you compare the linear motion and angular motion, linear motion is controlled by its inertia measured in terms of mass, not exactly in terms of mass, but a quantity related to mass. Likewise, the rotational inertia is understood in terms of a quantity known as moment of inertia. It is represented in terms of moment of inertia. Moment of inertia is basically a tensor, but for a fixed axis it is scalar quantity. Now let us consider a point mass. For example, let us consider this structure. Here is the axis of rotation. Let's assume that this is the axis of rotation, and a particle is capable of going round in this circle at a distance r. Mass is m. Then the moment of inertia is given by m into r square. Moment of inertia is given by mr square. Suppose I consider a couple of particles, for example, a particle of mass m1 at a distance r1, m2 at a distance of r2, m3 at a distance of r3, etc. present. Then the moment of inertia of this system is given by m1 r1 square plus m2 r2 square plus m3 r3 square, etc. So this is the moment of inertia of a system of discrete particles. Moment of inertia of a system of discrete particles. Now the question is, what if the object is a continuous mass system? For example, here is a continuous mass distribution and it is rotating about this axis. Then how to do that? I will take a small mass dm. Let's assume that it is at a distance r. Then the moment of inertia of this small mass is given by dm into r square. So the total moment of inertia is given by integral dm into r square. So moment of inertia of a continuous mass distribution is given by this particular idea. I is equal to integral dm r square. This idea actually takes us to the idea of radius of gyration also. So what is radius of gyration? Radius of gyration is the distance at which the mass is assumed to be concentrated such that we get the same moment of inertia. So we get the same moment of inertia. So we choose that point in such a way that the moment of inertia obtained is same as before. That means we can write I is equal to mk square. For example, if I want to replace, say, this extended object by a point mass, and if k is this distance, then k becomes the radius of gyration. So the requirement is that this particle and the replaced mass or the extended object should have the same moment of inertia. So basically radius of gyration is nothing but I divided by m, where I is the moment of inertia of the given object and m is the mass of the given object. There are two important theorems as far as moment of inertia is concerned. One is what is known as theorem of parallel axis, and the second is theorem of perpendicular axis. Let's see what is that. According to parallel axis theorem, suppose I know this moment of inertia of an object about its center of mass. I will call it as ICM. I can find out the moment of inertia about any other axis. How? About any other axis, the moment of inertia is moment of inertia through center of mass plus mass of the object into separation between these two parallel axes square. So I is equal to ICM plus MD square, where ICM is the moment of inertia through a parallel axis passing through the center of mass, and D is the separation between these two parallel axes. So according to parallel axis theorem, the moment of inertia of an object about any axis is equal to sum of moment of inertia about a parallel axis passing through the center of mass and the product of mass and separation square. Which separation? Separation between their axes. Second is theorem of perpendicular axis. Theorem of perpendicular axis. This is applicable only for planar objects. For example, let me consider a planar object, maybe in the form of a plate. Moment of inertia about this axis, the axis which is perpendicular, is equal to sum of the moment of inertia about other two perpendicular axes and passing through the same point. Means if I call this as say x axis, this as y axis, this becomes z axis, then Iz is equal to Ix plus Iy. Iz is equal to Ix plus Iy. Remember two things, this is valid only for planar objects. Moment of inertia of a planar object about an axis perpendicular to the plane is equal to sum of moment of inertia about any two perpendicular axes in the plane of the object and concurrent with the first axis, lying in the plane and concurrent with the first axis. This is perpendicular axis theorem. Let us take up moment of inertia of some standard objects. Worth remembering, moment of inertia about some standard objects. Remember, these are all important. For example, a point object. Mass is m, distance is r. So now moment of inertia is mr square. Moment of inertia of a rod. For example, this is the axis, assume this is the length, then moment of inertia is ml square by 3 about one end axis. Rod and perpendicular bisector, then moment of this is of course L, this entire length is L, so mass is m, moment of inertia is ml square divided by 12, ml square by 12. Solid sphere, about this diameter, the moment of inertia is 2 by 5 mr square. R is the radius. ring. About this axis, the moment of inertia is mr square. Disk, about this axis, the moment of inertia is mr square divided by 2. A rectangular plate. This is L and this is B, and this is the axis about which it is rotating. Then about this axis, the moment of inertia is ml square divided by 12. If I consider this axis, the moment of inertia is mb square divided by 12. So about an axis in its plane, it is ml square by 12 or mb square divided by 12. Same plate. This is the axis. Assume that this length is L, this length is B. Then about this axis, the moment of inertia is m into L square plus B square divided by 12. L square plus B square divided by 12. A circular hollow disc. Like this. This is of radius r1 and this is of radius r2. And the moment of inertia about this axis is m by 2 r1 square plus r2 square. M by 2 r1 square plus r2 square. That's the moment of inertia. Hollow cylinder. Of radius r, and assume that this is the axis of rotation, then moment of inertia is mr square. Same thing. This time the axis is different. This again is a hollow cylinder. Now assume that this is the axis of rotation. This is of length L, radius is R, etc. Then about this axis, the moment of inertia is m into L square by 12 plus R square divided by 2. Of course, this is a hollow cylinder, remember. Solid cylinder. About this axis, the moment of inertia is mr square divided by 2. Suppose I consider the same thing. Now the axis is different. Assume that this is the axis of rotation. L is its length, R is the radius, etc. Then moment of inertia is given by m into L square by 12 plus R square divided by 4. A hollow sphere. In the case of a hollow sphere of radius r, about any diametrical axis, the moment of inertia is 2 by 3 mr square. 2 by 3 mr square. So these are some important ideas which should be kept in mind. Remember these important things. They are useful while solving problems. One of the most important ideas as far as the competitive examination is concerned is that of rolling motion. What is rolling motion? Motion is said to be rolling if the point of contact is not sliding, we can say. It's actually pure rolling. This can be understood like this. In the case of sliding motion, the surface in contact keeps, or say the same surface of contact is seen all along. In the case of rolling motion, it's basically the point of contact. Object is said to be rolling if it is moving on a given surface. For example, I will take a simple example, maybe that of a cylinder. Now, if it is spinned and released, then it starts moving like this. This is an example of rolling motion, that of say bicycle wheel or say a wheel. Let's assume that this is rolling and r is its radius, m is the mass, and it is moving or say rolling at a constant angular velocity omega. If it is rolling at a constant angular velocity omega, so clearly it has two velocities. One is translational velocity. The center of mass is moving, it is in translational motion, and it is rotating as well. So the total kinetic energy comprises of translational kinetic energy plus rotational kinetic energy. Translational kinetic energy is half mv square. Rotational kinetic energy is half I omega square. Remember, this I is measured about the center of mass. V is the velocity of center of mass. So you can simplify it further. Actually, half m v cm square into 1 plus, I can write it as ICM into omega square divided by m v cm square. Half m v cm square 1 plus, ICM can be written as, what is it, mk square, correct, and VCM can be written as r square omega square. So ICM divided by, if we look at this term, this becomes ICM is mk square omega square m into r square omega square. M's cancel, omega squares cancel, and we are left with 1 plus k square divided by r square. So the total kinetic energy of a body which is in rolling is given by half mvcm square plus, into 1 plus k square divided by r square, where k is the radius of gyration. And it also has total angular momentum given by its translational motion, which is m into vcm into r, momentum into distance, linear momentum into separation, plus because it is rolling or rotating, it also has angular momentum given by ICM into omega. One of the important discussions here is that of pure rolling. Rolling is said to be pure if it does not slip. That means there is no slipping of the point of contact. Suppose I consider a stationary surface, then the condition for pure rolling is given by VCM is equal to R omega. And if it is accelerated, in the case of an accelerated motion, ACM is equal to R alpha. Now what if VCM is more than R omega? In that case, it is rolling with forward slipping. If VCM is less than R omega, then it is rolling with backward slipping. Rolling with backward slipping. And as we have already seen, the total kinetic energy is half mvcm square into 1 plus k square divided by r square. Remember this expression, a quite useful expression. One of the very important applications is pure rolling on an inclined plane. Pure rolling on an inclined plane. For example, you can consider, say, an inclined plane of inclination theta on which a sphere of mass m, radius r is released. It can be a sphere or cylinder or ring, anything, of course, anything that can undergo pure rolling. So some important equations which are worth remembering are here. Number one, acceleration A is equal to g sin theta divided by 1 plus k square divided by r square. Remember, in order that it undergoes pure rolling, friction has to be present. If friction is absent, there can't be no rolling, no pure rolling on an inclined plane. So, minimum coefficient of friction is given by tan theta divided by 1 plus r square divided by k square. Remember these results. As far as pure rolling on inclined plane is concerned, the acceleration is g sin theta by 1 plus k square by r square, and the minimum coefficient of friction is given by this value, mu minimum is equal to tan theta by 1 plus r square by k square. One of the very important applications of all these concepts is in the form of torque and the relation to angular momentum. Now, torque is given by I alpha, and this can be simplified further, I into d omega by dt, and this becomes d by dt of I omega. I'm just rearranging this. But you know, this I omega is nothing but the angular momentum. So, dl divided by dt. So, dl divided by dt. Or we have torque is equal to rate of change of angular momentum. So, if torque is 0, clearly dl divided by dt is also 0, or this gives us L is equal to constant, which is nothing but conservation of angular momentum. Conservation of angular momentum. Simple terms, if the external torque is 0, the angular momentum of the system remains conserved. Angular momentum remains conserved. Suppose I consider this torque, the torque does certain amount of work also. How to find out that? If we are supposed to calculate the work, the first thing is to check whether the torque is constant or torque is varying. If the torque is constant, we can simply write work done is equal to tau into delta theta, where delta theta is the angular displacement. Otherwise, it is written as integral tau d theta. Integral tau d theta. So, work done by this is given by this particular work done by the work done by the torque, that is constant torque or variable torque, is given by this expression. So, these are some important concepts as far as rotational motion is concerned. We will continue with numerical problems in our next session. This is crash course, and the chapter for our current discussion is gravitation. This small chapter is in fact an easy chapter, and in competitive examinations you can solve the problems pretty easily if you are familiar with some basic ideas. Let's take up those discussions and familiarize ourselves with the equations to be used. First of all, the idea of Newton's law of gravitation. Consider 2 point masses m1 and m2 separated by a distance r. Then, according to Newton's law of gravitation, the force of attraction between them is given by g m1 m2 divided by r square, where g is nothing but gravitational constant, and this force is always directed towards each other. This is an attractive force. Remember, as it is a conservative force field, mechanical energy is conserved. And remember, this is also a central force field. The angular momentum is also conserved. In order to understand the force, the idea of force, we need to understand it in terms of gravitational field. What is gravitational field? It is a region of influence in which another mass experiences a force. Couple of important relations here. Field due to a point mass. For example, here is a point mass m, and our intention is to get the gravitational field at this point P. Then the gravitational field at this point P is given by gm divided by r square. Gm divided by r square. What if I consider a spherical shell? Let us consider a spherical shell of radius r, and we are interested in finding the field at various points. For example, first point outside at a distance r. Then the gravitational field at a point outside is given by gm divided by r square, as if a point mass is located at its center. At a point on the surface, it is given by gm divided by r square, and at a point inside, the gravitational field is 0. Remember, the direction is always towards the center of the sphere. So, if we try to plot a graph of this gravitational field versus distance, it's something like this. Remember, it is always directed towards the center, so I am going to show it here. It's something like this. This corresponds to radius, right? It corresponds to this one. So, up to the center it remains 0, and outside it goes on decreasing as per 1 by r square relation. What if it is due to a solid sphere? Gravitational field due to a solid sphere. Here is a solid sphere of radius r, mass m, and the gravitational field at a point outside at a distance r is again given by gm divided by r square, as though a point mass is located at the center. At a point on the surface, it is gm divided by capital R square, while that at a point inside is given by gmr divided by r cube. R is this distance from the center, so gmr divided by r cube. So notice that inside, the gravitational field is directly proportional to its separation from the center. So if I draw gravitational field versus distance graph, is something like this. As you go from center towards the surface, the gravitational field increases in magnitude and it's directly proportional to r, reaches its maximum value, and it again goes on decreasing according to 1 by r square law. So it is 1 by r square law here, proportional to 1 by r square, and this corresponds to the surface, or the radius is r. Variation of acceleration due to gravity. Acceleration due to gravity is basically given by gm divided by r square. Suppose I consider at a height h, the acceleration due to gravity is given by g dash is equal to gm divided by r plus h whole square. And if h is very small compared to r, then we have g dash is equal to g into 1 minus 2h divided by r. Remember, conditions apply, h should be pretty small compared to r. At a depth, acceleration due to gravity at a depth is given by gm into r minus d divided by r cube, or this is given by g into 1 minus d divided by r. And remember, it is affected by rotation of the earth also. It is affected by rotation of earth. So due to the rotation, acceleration due to gravity is given by g minus omega square r into cos square lambda, where lambda is the angle of latitude. It's the angle of latitude. So g dash is equal to omega square, g minus omega square r cos square lambda, and of course omega is the angular velocity of the earth. Gravitational potential. Gravitational potential due to a point mass at a distance r. For example, here is a mass m and at a distance r we want to find out, then this is given by minus gm divided by r. Remember, gravitational potential is negative because the gravitational force is always an attractive force. Gravitational potential is negative. Due to a spherical shell. You got a spherical shell of radius r, then outside at a distance r it is given by minus gm divided by r, and inside at a distance r or on the surface, so I will write on the surface and inside, both are given by the same equation minus gm divided by r. So remember, the gravitational potential is constant inside a spherical shell. So if I plot a graph of v versus r, it's something like this. It remains constant at a value minus gm by r. Up to the surface it is constant. Outside it is 1 by r dependent curve. 1 by r dependent curve. What if I consider a solid sphere? But a solid sphere of radius r whose mass is m, then at a distance r outside, gravitational potential is minus gm divided by r, and that on the surface is minus gm divided by r. Well, that inside is given by minus gm into 3r square minus r square divided by 2r cube. Assuming, of course, the density to remain constant. So if I plot a graph of V versus R, the nature of the graph is like this. At the center, if I put R is equal to 0, it gives me 3 by 2 times the potential at the surface, and it changes like this up to the surface. This is minus 3 by 2 gm divided by r, and it is minus gm divided by r at the surface, and then it goes on decreasing according to 1 by r relation. So it is proportional to 1 by r. So the variation of the gravitational potential is given by this expression. Due to a thin ring, for example, you got a thin ring of mass m whose radius is r. Then at a point distant x from the center, it is given by minus gm divided by square root of r square plus x square. What about at the center? At the center, I can put x is equal to 0, and I am left with minus gm divided by r, which means that this is as good as the potential due to a point mass located anywhere on the circumference of this one. That's right. So it is as good as the idea of potential due to a point mass. So there are some basic ideas regarding the gravitational potential. Let us consider the idea of satellites and the idea of energy. Let us consider a planet of mass m and radius r. Then escape velocity from the planet is given by square root of 2 gm divided by r. Suppose I consider the orbital velocity. That means there is a low orbital satellite, then the orbital velocity is given by square root of gm divided by r, or this can be written as square root of gm divided by r plus h. This is our expression for the orbital velocity. If h is very small compared to r, then this expression reduces to orbital velocity is equal to square root of gm divided by r, or this is as good as escape velocity divided by root 2, escape velocity divided by root 2 from the surface. Let us consider the same thing. M and r are the mass and radius of the planet, and here is a satellite. The time period of this satellite is given by 2 pi r divided by v as expected. This is r, 2 pi r divided by v. And that can be simplified further. You can find that value of, substitute for that value of v over here, and it becomes 2 pi into r root r divided by root gm. 2 pi r to the power of 3 by 2 divided by root gm. If I consider the same satellite, its energies are like this. First of all, potential energy. Potential energy is given by minus gmm divided by r, and kinetic energy is given by half mv square, and if I substitute for that v, I get gmm divided by 2r. And therefore, what is the total mechanical energy? The total mechanical energy is U plus K, which is minus gmm divided by 2r. So these are the important energies of a satellite. Also remember, sometimes the questions are asked as what is that binding energy? Very simple. Binding energy is the negative of its total energy, which simply is gmm divided by 2r. Kepler's laws deal with the motion of the planets around the sun. There are three laws. The first law is known as law of orbits. According to which the path is elliptical and the sun is at one of the foci, or say it is at one focus. That is first law. So according to first law, the planets revolve in elliptical path with sun at a focus. Second law is law of areas, according to which the aerial velocity is constant. What is that aerial velocity? It is the rate at which area is swept. That is nothing but dA by dt is constant, and this is equal to L divided by 2m, where L is the angular momentum, Third law is the law of periods, according to which the square of the period is directly proportional to cube of the mean radius. What is that A? A is actually R max, semi-major axis, and semi-minor axis come here, R max plus R minimum divided by 2. Many times for circular orbits it becomes very simple. For circular orbits it is t square directly proportional to r cube. But remember, this is actually the mean radius. A is nothing but the mean radius. So mean radius cube. So remember these three laws. These are quite important for solving numerical problems. We will continue in our next session, in which we will apply these concepts to solve numerical problems. Thank you very much.